I'm Jiang Zhang, a PhD student from University of Southern California, supervised by Professor Konstantinos. Today, I will present our work, HARPO, Learning to Subvert Online Behavioral Advertising. This is a joint work with Harun and Professor Subvert from UC Davis. My presentation will consist of the following parts. First, I will give a brief introduction about online behavioral advertising. So as we know, nowadays, online behavioral advertising relies on privacy-invasive tracking techniques for user profiling and the subsequent ad targeting. And it poses a real privacy threat to web users. Existing privacy-enhancing tools can be classified into three categories. The first one is called privacy by design. Some big companies like Apple can allow users to opt in or opt out of tracking for some apps. However, it's mainly designed for iOS. And the second solution is blocking, which is defensive. There are lots of popular blocking tools like ad blockers. The users can try to block all the ads or trackers. However, the blocking tools can be circumvented by trackers easily. And more importantly, it will kill the advertising ecosystem if all the users try to block all the advertiser and the tracker. And the last solution is obfuscation, which is offensive compared with blocking. There are some popular obfuscation tools like TrackThis and Ad Nauseam. And compared with blocking, obfuscation tools are more ecosystem friendly. However, existing obfuscation tools are not principled and stealthy. Before presenting our solution, we will first describe our threat model. Our threat model involves two parts, the user and the tracker. The user will browse the web pages one by one, and the tracker is a third party, which will perform content-based user profiling and the subsequent ad targeting. Without any obfuscation, the tracker will know all the web pages visited by users, so privacy leakage can happen, since trackers can know all the user interests. Therefore, to reduce such privacy leakage, we assume that the user will mislead the tracker via an obfuscator. And we expect the obfuscator should be seamless, which means if the user tries to use this obfuscator, it will not affect the user experience. And it should be stealthy, because we don't want the tracker to detect the usage of our obfuscator. And finally, it should have low overhead, because we want to minimize the number of obfuscation URLs. And we also make two strong assumptions for our tracker. First, it has complete coverage of a user's browsing history. In practice, it can be achieved by cookies or cross-site tracking techniques. And also, we assume that the tracker has substantial computation resources to train machine learning models for tracking. Specifically, we consider two real-world tracking models. The first one is the user profiling model, where the input of this model is the user persona, which means the user's web browsing history. And the output are interest segments. And we choose the Oracle data broker as our real-world user profiling model, since it's public available and it combines data from more than 70 trackers. And here are some examples of the interest segments by Oracle data broker. You can see that there are lots of categories, subcategories, and for user profiling, which can capture your interest in a very detailed way. And the second model we consider is the ad targeting model. Still, the input of such a model is the user persona, and the output are the bid values placed by different bidders during the online behavior advertising. Note that ad targeting model can be a subsequent step of user profiling model, because in order to determine the best bid values during advertising, the bidders need to know the user profiles in order to optimize their bid values placed. Now I will present our solution, HARPO. At high level, HARPO interleaves web page visited by users with obfuscation URLs. Specifically, it starts by extracting the content features of the web pages visited by users and featureize them using embeddings. The reason that we want to extract the content of the web page is because in our threat model, we assume that the user profiling model is based on the content. Next, we train a reinforcement agent to select the obfuscation URLs in order to optimize a reward. So the reward here will be any one of the privacy metrics we defined later. So once we train this reinforcement agent, it will select these obfuscation URLs, and we will send them to the URL agent, which will inject these obfuscation URLs into users' web browser history in order to distort the tracker's view. Now I will present our privacy metrics defined in order to optimize the obfuscation URL selection process. So we first define two metrics for the user profiling model. The first metric is defined as a percentile of false interest segments after obfuscation. Basically, these privacy metrics capture the false positive rate of this user profiling model after you do any obfuscation. And the second privacy metric is defined as the number of different segments before and after obfuscation. Basically, it wants to capture the number of segments added and also the number of segments removed after you do obfuscation. We also define two metrics, privacy metrics, for the ad targeting model. The first metric is a percentile of increased high bids caused by obfuscation. And the second metric is the average bid ratio, the average ratio of bid values after obfuscation over the one before. As we mentioned in our threat model, the ad targeting model is a subsequent step of user profiling model. So if we can try to distort the bid values placed by bids, then actually we are trying to distort the advertiser's confidence about the user profiles they build. For example, if we try to trigger high bids, which are if we make the advertiser to play high bids on some ads, which are irrelevant to the user's interests, then it actually provides privacy benefits to users. So that's the reason why we define these two metrics for the ad targeting model. Next, I will present our system model. At high level, we model the obfuscation URL selection process as a Markov decision process. The state in this MDP is defined as the visited URLs up to obfuscation step T, and the action is one obfuscation URL category. The reward here is defined as the difference of any one of the privacy metric before and after obfuscation step T. And finally, the policy for this MDP will output the probability distribution of obfuscation URL category. Finally, I will present our detailed system design of HARPO, which consists of 4 modules. The first one is the content feature extraction module, which will convert each URL into an embedding. The next one is the reinforcement agent. Because in our Markov decision process, we have huge state and action space. So in order to find the optimal policy for this MDP, we use reinforcement learning. And therefore, we model our obfuscator as a reinforcement learning agent. And our policy is modeled as the convolutional neural network and the LSTM neural network. And we train this RL agent use A2C algorithm. We provide lots of technical details in our paper about how to train this RL agent. And the third module is a surrogate model, which is used to replicate the real-world user profiling and ad targeting model. So the reason we want to design such a surrogate model is that we want to use it as a virtual environment for efficiently training our RL agent offline. Because in practice, it's really time-consuming to keep collecting feedback from the real-world tracking systems. So that's the reason why we first collect some data, train a surrogate model, and use it as a virtual environment for efficiently offline training of our obfuscator. And finally, we have a URL agent, which is implemented as a HARPO browser extension. And to evaluate and to train and evaluate HARPO, we first need to collect some user persona data. In total, we construct 25,000 user personas, while 10,000 for surrogate model training and 15,000 for our agent training. And we use OpenWPM for user persona construction. Once we constructed the persona in lots of broader instances, we will then collect the interest segments and bits from the real-world trackers. Specifically, we collect the interest segments by visiting the Oracle data brokers. And we also collect bid values from 3 popular header bidding enabled bidding sites. Once we collect this user persona data, we first train our surrogate model. In total, we get 20 user profiling surrogate models. For each of these surrogate models, it can predict whether an interest segment can be triggered by the input user persona or not. And in the average true positive rate for these surrogate models is 96%. And also we have 10 ad targeting surrogate models. For each of these surrogate model, it will predict whether a bidder will place high bids given an input user persona and an ad slot. So we report that the average true positive rate for this ad targeting model is 73%. So the takeaway here is that our surrogate models can replicate the real-world tracking models very well. Therefore, we can use it as a virtual environment to train our obfuscator offline. So once we train our obfuscator, which means the IR agent, we will evaluate it in real world. Specifically, we will send a set of obfuscated personas to HARPO, and it will generate some obfuscated personas. Then we will construct these personas in real world and do the evaluation from 4 aspects. So first, we will evaluate the HARPO in terms of the privacy. So this table shows our evaluation results. So against the user profiling model in the real world, we can see that after obfuscation, HARPO can trigger more than 43% false segments. And also, HARPO can trigger around 4.2 different segments. And compared with all the baselines in prior works, HARPO can outperforms them by almost 3 times. And also, against the real-world ad targeting model, we report that HARPO can trigger on average more than 43% high bids. And also, HARPO can trigger around 17% higher bid values. And finally, HARPO can outperform all the prior baselines by up to 16 times. Next, we evaluate the overhead of HARPO. First, we evaluate the obfuscation overhead in terms of the percentile of obfuscation URLs. So if we look at the figure, the red column means in the user persona, there are 10% obfuscation URLs. And for the red columns, it means that in these personas, there are 20% obfuscation URL. We can see that HARPO can achieve the same level of privacy with 2 times less overhead. And for the system, next we evaluate the system overhead when alpha equals to 0.1. So we can see that both the page load time and the system resource usage are very small if we use HARPO. So hence, we conclude that HARPO has a minimal impact on the overall user experience. Next, we evaluate the stealthiness of HARPO, because in practice, the tracker may run some fraud detection to detect the usage of our HARPO. Specifically, we train an adversary detector to detect whether the input user persona contains any obfuscation URL or not. And here is our evaluation results. So in the top right region of this figure, it means high privacy and stealthiness. And as we can see, in general, if we increase alpha, which means the percentage of obfuscation URLs, we can achieve high privacy while less stealthiness. And if we look at the blue curve of HARPO, it can dominate all the curves of all the other baselines, which means HARPO can achieve better privacy and stealthiness. And finally, we evaluate the personalization effects of HARPO. Because in practice, users may disallow HARPO to distort certain interest segments. Maybe the user want to preserve some segments to receive related ads, or maybe they don't want to receive some weird ads after obfuscation. So that's the reason why we train HARPO to distort allowed segments while preserving the disallowed segments. As we can see, after personalization, HARPO can achieve the same level of distortion in allowed segments, while we reduce the distortion in disallowed segments from 0.7 to 0.1. Before the end of this presentation, we will introduce our HARPO extension. It consists of a JavaScript front end and a Python backend. Yeah. So the front end will send the obfuscation URL request. And the back end will run the machine learning model to decide the obfuscation URL selection and send it to the front end. The front end will visit the obfuscation URL. And this is our user interface. And you can view your snapshot of your interest segment. And also you can choose to opt out some obfuscation URL categories for personalized obfuscation. So in conclusion, we propose HARPO, a principled learning-based obfuscation approach for online behavior advertising. And we released our code there. And what's next? We want to design a utility-preserving obfuscation approach. So thanks for attending. Any questions?